Scalability matters. Modern software seems to have to deal with ever larger amounts of data, and it's no use having a program that works just great with a small amount of data, but slows down as you add more data to such an extent that eventually you never get a result. One of the tools used to investigate scalability is Big O notation. This video is a follow-up to one where I investigated the time behavior of different structures used in a first in, first out, or queue-like scenario. That investigation was made from a theoretical perspective. This time I'm going to demonstrate the actual performance of these structures. In this practical example, we're going to run a simple test of first in, first out throughput on 5 structures. These will be the ArrayDec and linked list classes from the core Java libraries, both of which implement the DEC interface directly, a homemade circular buffer, and 2 linear array-based structures, one homemade and the other a wrapper around the array list of the core Java libraries. The simple test treats all the structures as implementations of the DEC interface. We'll put a number of items into the structure and then pull those items out. I'll be treating the DEC as a single-ended queue since all of these structures can be expected to perform similarly in both directions. Here's the code for the core of the exercise. The method addAll then removeAll inserts count items in a series of addLast calls. Each item added is the integer 0 that was created and initialized here. The reason for this is that we don't want memory allocation and garbage collection of the data to influence our test results, so we use the same object and therefore the same reference value every time. If the structure itself performs allocations, which is the case for the linked list, that's different of course. We need to see that in our results. In the next step, the code removes all of the items with a series of calls to remove first. We're trying to measure the performance of individual add and remove operations, so we call those individual operations many times, rather than perhaps using any kind of bulk operation that might be more efficient for this particular scenario in a production environment. Recall from the qualitative description in the other video that if we're doing this with a linear array type of structure, there will be copying going on here for each remove first operation. The amount of copying will be in proportion to the number of elements still in the queue. The time taken by addLast will be unaffected by the number of elements in the structure. In this direction, remove first is the ON operation. If instead we used add first and remove last, then the add first would be ON and the remove last would be O of 1. Also, if we have a dynamically sized array, it will potentially grow and shrink many times. Each resizing operation, of course, involves additional copying and some memory allocation for the new array. We'll see that this doesn't seem to have a big impact in these tests. I have 5 different structures to test with this exercise. Each structure implements the method of the DEC interface that are actually used in this test. I didn't code up all the methods of the interface. Of course, 2 structures, the linked list and ArrayDec, already implement the DEC interface fully, so I didn't have to do anything about those. The bottom line is that all 5 can be tested with the same code without going crazy over the implementations. The first structure is a homebrewed structure built on a linear array. We don't expect this to have great performance. Well, I wrote it, but more seriously because it will involve a lot of copying. This one I called LBuffer. Let's take a look at the code for this. We have the array that stores the data and a counter that indicates how many of the slots in the array are in use. Notice we'll be filling this from the 0 index towards the higher indexes. You can see that here in the addLast method. We insert the item at the index of count and increment the count variable ready for what happens next. The code will simply crash out with an exception if the structure is full. The remove first operation throws an exception if there's no data, and otherwise we'll take an item from the front of this array. Then the contents of the array must be shuffled up by one position, and that's the job of the system.arrayCopy operation here. Notice that we reduce the count by 1 before doing this. We only copy the data items that are still meaningful. We're starting at index 1 and moving that down to index 0. Also, this structure does not grow or shrink the storage array, so the only copying operation will be in the removeFirst method. The next structure is a simple wrapper around Java's own array list. The wrapper simply allows the array list to fake being a deck for the small number of operations used here. I used Java 21, and in that release there are new methods called addLast and removeFirst. The array list still does not implement the deck interface. These new methods are part of an interface called sequenced collection that's also new with Java 21. But they make a very easy delegation target and do exactly what I wanted for our test. The next structure is the homebrewed circular buffer, cbuffer. This has a simple array for the data and a capacity which will be one less than the size of the array. We also have the head and tail index values. Head is the place where the removeFirst operation will take data from. But this is only possible provided the structure isn't empty. Remember, we indicate empty when head and tail have the same index. Tail is the index of the location that will be stored at by the next addLast operation. Before we attempt to do an addLast, we first check what the value of tail would be after that insert. If it's equal to head, we're already full and the add must be rejected. Here's the code that implements the test. It throws an exception if the test shows we're already full. If there's space, we store the new data at the original tail index and then bump the value of tail to the next empty space. Of course, the point of the circular buffer is that we wrap the linear list up in a circle. So incrementing either head or tail must be done in such a way that when we increment past the capacity of the storage, we start again at index 0. This is a modulo or remainder operation. Java actually provides remainder, but modulo and remainder are the same for positive integer operands that we're working with. Here's the calculation, which was implemented in this function nextIndex. The next two structures are the library linked list and the library array deck. Recall from the theoretical discussion video that the array deck implements a circular buffer similar to the one I created, but likely with more refined code. These structures already implement the deck interface and are used here without change. We'll run the tests on each of these, but let's take a look at the test code. There are several practical difficulties with performance tests like these. One is simply that I'm running this on a machine that has 1,000 or so operating system level processes that are also running. Those will sometimes demand more CPU and slow the code under test down. That level of jitter is usually not great, but there's another, sometimes quite significant concern. The JVM provides a just-in-time compiler. That is, when the code starts, it runs as interpreted bytecode. As it runs longer, or more precisely as the same chunk of code runs more iterations, the system compiles that bytecode down to a machine-specific binary. That, of course, results in a significant speed-up in execution. We need to run the code enough times that this optimization has completed and we've averaged out the variations due to other operating system activity. To achieve this code runs our exercise method repeatedly, capturing the time taken for each iteration, until 5 iterations in a row produce similar execution times. Here's the code for the loop that requires similar timing before completing. The test method, addAll then removeAll, returns the time that elapsed during the test. Each time, we calculate the percentage difference between this execution and the previous one. The first time around we have no previous time, so we fake it by pretending it was the longest time we can possibly represent. We also print out the time of the last and current tests and that percentage difference. Where the difference is less than 1%, we consider the two tests similar. But if they're more different than that, we reset the count of similar results to 0 again. So let's start the test with 2,000 data items and exercise the home-brewed linear buffer. This, of course, has lots of copying. We can see that the times are quite short, around 160 to 170 microseconds. By the way, with tests this short, if we run this several times, we'd likely to get a wide variation between results. The rate of data moving is about 12 million items per second. If we increase the data to be copied to 20,000 items and repeat the test, we see that the times taken have increased about 100-fold. Well, we have 10 times as much data, so 10 times as long would be expected anyway. But because of the copying, that's the O of n performance factor, each item moved takes 10 times longer. We see that the rate of transfer has decreased by a factor of 10 from about 12 million per second to 1.3 in this case. Let's do it again with another 10x increase in the amount of data. Again, the times have increased 100-fold and the throughput has reduced by a factor of 10 to about 140,000 per second. Keep in mind these numbers are still approximate. If we ran the same test twice, we would not get identical values. But I think it's clear that the O of n characterization of this structure is valid. We lose performance in proportion to the number of items in the structure. Now, let's see how fast things go with other structures. We'll change back to the 2,000 item count and select the wrapper around the array list. This is a very similar structure to the linear buffer I wrote. When we run this, we get about 12 million items per second. Very similar performance to the code I wrote. When we change this to 20,000 items, we see the throughput again reduced by a factor of 10. And with the data set to 200,000 items, we get another reduction tenfold. Okay, again we'll set the data item count to 2,000, but now we'll select the circular buffer that I built. This seems to be much faster, at about 125 million item pairs per second. But, more importantly perhaps, if we change the data count by a factor of 1,000, that's 10 times the amount of data we ever copied through the linear structures, we see that the throughput rate is pretty much unchanged. The time has grown in proportion to the data, but that's expected. We performed 1,000 times as many operations. The point here is that each individual operation was not slowed as a result of the larger data set. That is the effect we expect for an O of 1 operation. Now let's go with the linked list. We'll also configure 2,000 data items. Here we get about 140 million operations per second, a little better than our circular buffer. Increasing by a factor of 10, the throughput reduces to about half, not quite 67 million. Interesting, we think this is an O1 operation, at least at first glance. Remember, we're accessing the head and tail, and this is a doubly linked list, so no link traversal is needed. Let's try this a few more times without changing anything. 164, almost 64, almost 164, and 121. It seems like this is very much less consistent than the other models. Let's try again with another 10x increase, bringing the count to 200,000 data items. Running this several times, now it seems to be a bit more consistent. The rate seems to be near 70 million per second. My guess is that this is because there's much more memory allocation going on. Not for the data, of course, that's just a constant object we keep reusing, but for the wrapper objects used by the linked list that contain a reference to the data item and the next and previous data items. The two more important observations here are perhaps that first, this does appear to be characterized by O of 1, a constant time operation, and that simple timing tests of Java code can be quite inaccurate unless you have enough iterations being tested to get a truly representative average result. As a side note, I've had the garbage collector configured to print messages about its activity all along. Up to here, we've really not had any output from it. But in this case, we see some messages from it. There are a couple here. the second of which shows a GC operation that took 9 milliseconds to complete. Here's another one, taking just over 2 milliseconds. In reality, though, these times are not particularly significant part of the overall time. I think this particular sequence ran the test about 50 times at 3 milliseconds each time. Okay, let's move to the array deck and go back to 2000 data items. This seems to have a much higher performance, 450 million items per second. Let's increase that by a factor of 1,000 and bring it up to 2 million items. We're still getting 200 million items per second. And remember, that includes the time to allocate the buffer. If we increase the data size another 100 times, bringing it up to 200 million items in the buffer, we see that the allocation of that memory block takes a moment. But then the data transfer rate through the deck structure is still around the same overall throughput of 200 million pairs per second. So there you have it. An array can be an excellent or terrible way to build a FIFO queue, depending on how you use it. The problem with the linear approach isn't that it's slow all the time. It has a decent performance with small amounts of data. Rather, it's that the throughput drops off in proportion to the number of elements in the queue. And that means its scalability is poor. This is only O of n. Many algorithms, such as sorting, scale worse than that. But the constant time behavior of the circular buffer certainly wins and should, for the use pattern tested here, be the obvious choice for scalability. Of course, by that I mean use the ArrayDeck library feature. Don't go writing it yourself. Also, don't forget that poor scalability might be less important than fast performance if you know you'll have small amounts of data. Okay. That wraps up this video. If you found it interesting, please don't forget to subscribe and leave a comment. Perhaps you'd like to suggest a topic for a future video. Cheers.